So, yeah, to all the audience of this podcast, thanks a lot for your interest. I'm Dhavala. I'm a postdoctoral fellow at Technical University of Munich, and with me is Naman Jain, who is a doctoral student at Max Planck Institute for Quantum Optics. So, in this series, as you all know from the previous conversations, that we will be talking to women scientists and educationalists who have contributed to the community in their own way, and they have a story to share with us. So, the message we are trying to convey is that any of you who is listening to this podcast and wants to pursue science or academia as your career, you can do it. And the experiences of the people with whom we are talking in this series or otherwise are kind of a guideline to shape our thoughts, and it also helps us to take informed decisions in crucial points of our lives. So today we are talking to someone whose expertise is in one of the hot topics of present times, which is quantum information. We hear this word a lot, perhaps a lot more than what we understand. And she's the right person to kind of ask questions and get our confusions and misconceptions a bit off the mark, I suppose. So she has had an interesting career, beginning with St. Stephen's College. Sorry, am I right? Okay, so beginning with St. Stephen's College, Delhi, she passed through IIT Delhi, Yale University, and MIT in various stages of her academic path. Now she's a professor at UMass Lowell, leading a group called Quantum Engineering Science and Technology. So each of these words have quite a deep impact in present times, and let's know more about what she has to say regarding her field and her life. So without much ado, welcome aboard, Archana. Thanks a lot for being with us today.
Thanks a lot, Dhavala and Naman, for inviting me. Yes, I look forward to this conversation and being part of this effort called Zeroing In.
Yeah. So we typically start this conversation learning from how it all began. Rather, we would like to typically know, how was your childhood? Where did it start? And can you tell us a bit about your childhood and the kind of academic atmosphere you were in?
Sure. So I grew up in Delhi. I was born in Delhi. I grew up in Delhi. Both my parents were working. So of course now they're retired, but at that time we were working, and it was actually it was actually very unusual for that time, in the sense that most of the mothers of my classmates were not working. Like, it's very typical, right? They are like in middle class India, where the father works, the mother is a homemaker, and I actually used to resent that a lot. That why is my mother working? So in fact, as a child, it might sound very counterintuitive. My dream was to become a housewife. Because just because I thought, oh my God, this is the best job in the world. Like, when my children will come, I'll be at home, and I could see my mother doing this, trying to manage like, my father was a big help actually. They used to work a lot together in the kitchen and everything. So it was not that she was doing it alone, but still it was very hard because she was actually in corporate finance and banking. So she had very long hours. So she would come, and then you have to make her food. And at that time, at least, it was not just like, there was no Uber Eats. You can't just order food. When you come back, you have to still make the whole food, and especially when you have a family. So I used to think, oh my God, this life is too hard. I would just have a great education, but then I will have like 7, 8 children and just be at home. That was my, but of course, my parents were actually, my father is an endocrine, was a practicing endocrinologist. And so he was the main influence in terms of trying to go into sciences for me. And my mother actually was kind of a math prodigy in her time. So she was much more into like going into mathematical sciences. So mathematics and sciences, it was like, either maths or physics would be probably what I would end up doing. But what was happening was, I think in India, at least at that time, I don't know if that has changed. If you're really good in studies, you take sciences. But my mother was exception to that rule, right? And because she was absolutely at her time, there was no non-medical science. There was either medical science or commerce. So she has a absolutely morbid fear of anything to do with blood or dissection or anything. So she's like, I can't do medical science. So she actually, despite being very good in her studies, did opt for non-sciences. So it was her dream that maybe I will do something mathematical in sciences. So in our school, though, they were like, no, we don't subscribe to this viewpoint that, brighter students should take science and not so bright students take humanities. That was not. We are going to actually do an IQ test of all the students. And we will also do aptitude tests of all the students. And based on these IQ and aptitude tests, we will try to at least guide them what they should be doing in their future. Okay, it's up to them, of course. This is
quite advanced, I would say. I mean, it's not.
It was very progressive, but they were not progressive enough to have humanities as an option because humanities students bring down the school average. That's why I say. So it was progressive in that limited sense of the word. That we will be very progressive, but no humanities because because then our school result will go down. It's like progressive enough.
Yeah.
But anyway, so coming back to the 10th class thing, when we were this aptitude and IQ test. So I scored very high on IQ test. You shouldn't read too much into it for the simple reason when my mother and father got to know about my IQ test, they were actually surprised. And I was annoyed by the surprise. I was like, what did you think? So I'm just saying the people who knew me most closely were actually a bit surprised. I don't think that they thought that it was dumb, but I guess there was not a number which was put on that front. And for people who do not know, this IQ test don't have a scale. So how much importance you attach to a scaleless number, you should be careful about that.
Yeah.
But my bigger worry was that there was an aptitude test where you have to look at what kind of things appeal to you, like fine arts or sciences or engineering or something like a creative writing or things like that. So when my school counselor called me in her office because they had like a one-on-one session with the counselor. It was actually, as I said, very progressive for the time because there didn't used to be school counselors in normal schools at that time. So that's why our school was actually kind of ahead of its time in that sense. And they had a 15-minute one-on-one session with every student of class 10. So the charts of the aptitude tests were there because she first informed me of IQ and then she's like, yeah, so you'll probably do well in whatever field you choose. But anyway, let's see which field you want to do. And all the other people, they had their aptitude tests and they looked like, Himalayan peaks. They were so high aptitudes and everything. Then she pulled out my aptitude sheet and it looked like an ECG of a dying man. It was like flat. And then there was a small blip. And that blip was near administration.
And
I was like, oh my God. She's like, yeah, that's very weird. It's like you have an aptitude for administration. And I immediately thought that I will become some old maid, sorting through files in some old office. Because I don't have aptitude for anything apparently.
I see.
So I was actually very dejected and she could immediately see that I'm becoming very, I was a bit shocked at my lack of aptitude. Completely. So she basically kind of consoled me. I will cut the story short and basically said, even though I have an aptitude-less brain, given how high IQ I have, maybe if I try hard, I will develop some aptitude for something. Because my IQ will help me, I won't fail. So maybe if I keep doing well, no matter which field I choose, because I keep doing well due to my IQ, maybe, my aptitude-less self will find it. So that was The whole conversation ended in, I think, 8 minutes instead of 15 minutes because I was not saying anything. I was like, should I take it again? That's what I wanted to ask her. Like, no, this is fine. This is what it is.
So it really tells us that, you cannot associate meanings to these scaleless numbers and some random tests and so on, and let some random things judge our interests.
Because I don't know, as a 14, 15-year-old, you're kind of, I don't know still what I did out on that aptitude test that I got that. But anyway, so I did end up taking medical science. So I had biophysics, maths, and chemistry, along with English. And I think I did not, by that time I realized that I don't want to do engineering because I think with PCM, as they say, you can even go for engineering, but I think engineering was a little dry for me. No offense to engineers, it's fantastic. But in this, so then I think I was, I did sit for competitive exams in medical science. Sadly enough, I didn't make through AIMS, which is very competitive, but I did, I think, get into some kind of a, what's that thing called? It used to be some all India PMT thing, and you can get placed somewhere. And I was, I think I would have needed to leave Delhi. And that time I was very protected as a child. So I was like, no, I'm not going to study medical science away from my parents at this stage. So the next, of course, thing was like I got accepted into BSc Honors Physics, and I think and Maths at St. Stephen's, and then I just flipped a coin and decided to do physics. Basically, it's not very stroke of like inspiration in that sense, but that's how I started doing physics.
St. Stephen's has the history of producing plenty of scientists or physics and mathematics. It's like the place of just about anyone. If you just say St. Stephen's, you might be right. So,
but well, interestingly, also administrators.
Absolutely,
that's true. That's true.
Yes,
maybe even politicians. No?
I actually, when my parents saw that, they were very supportive. That's why I think they were like, "Oh, you can become an IAS officer."
Right?
You will get a car with a revolving red light. Like, maybe that's not such a bad idea.
Civil service. So.
No, but you're absolutely. So I think actually, to come back to your point, Dhavala, I think in St. Stephen's was the first time. Because, okay, in the spirit of full disclosure, the physics which we are taught in high school is absolutely uninspiring. Okay. I did not enjoy it. Because I remember, what was that time? Pradeep's. There was this thick book. And modern ABC physics and all that. Oh my God. And then like there's a pulley here and there's a pulley there and there's a mass there. And then if you pull on that mass, how much will be the tension on that? I honestly did not.
It's quite surprising that you still remember it. Definitely makes the point that you definitely did read it enough.
This is all PTSD, post-traumatic stress. You never forget that. I'm just trying to say, I think what we teach physics in classrooms has very little to do with physics in research. And the first serious exposure to physics you get is in your high school, right? Because before that, there is no separation of physics, chemistry, and biology. It's just taught together in some sense of science, right? You have one single exam. The first time you kind of have a specialized knowledge of these subjects in high school. And it's not a problem of mine. We had very excellent teachers. The content was very dry. And I think the fact that it was convolved with like preparation for competitive exams made it very like the focus was on speed and accuracy. Like you not only have to solve the question, you solve it fast, right? And CQs and all that. I still remember. I'm seriously. And so how do you get time to enjoy anything?
Exactly.
Because the whole focus is on being fast and quick, and it was easy for people like good students, and I was fortunate enough to be part of that. But it was really not enjoyable. You're just good. Just because you're good at something doesn't make you enjoy it. So in some sense, the first time I really enjoyed physics and appreciated it as a subject was in St. Stephen's. Because all our teachers were PhD in physics themselves, so they would kind of inspire us. And I still remember that. Our head of the department said, you might not do physics after BSc Honors. You might do MCAs, MBAs, and engineering, whatever, because were some people who wanted to still do engineering entrance preparation because the poor guys couldn't clear engineering.
Okay.
So BSc honors 1 year.
Yeah.
Instead of sitting empty at the house, let us try it. That kind of. So physics was like a refuge for engineering rejects for some of them, even though they were in St. Stephen's, which is a premier college. That you can't change that. But it was very clear. It was like our job, our intention of teaching you in BSc honors is that you will go on and do MSc physics. That is the aim of BSc honors, to prepare you for MSc. You may not want to do, but that is exactly why we are teaching you physics. To basically give you a foundation of physics so that you can continue your studies in this subject. You may not want to do that. And in fact, he was right that only very few people in our batch did continue with physics, and most of them did not. But it really helped me to really appreciate the subject. We had like a year-long training in every subject, and the university exams used to be happening annually. So there was a lot of time to actually explore subject in depth and detail. We had some absolutely fantastic teachers in Stevens. So that time I was like, maybe that's not a bad idea. Like this can be done for something. I still did not know what I wanted to do, because when you talk to so my parents were again very supportive. They were very proud that I'm doing BSc honors from Stevens. I think they never let me feel that I have not cleared the AIMS exam.
The JEE or sort of
because the JEE was never on the horizon because I didn't want to do engineering, but AIMS nahi kiya.
TMT.
But they were actually very proud, so I felt very valued, very like a achiever in terms of doing physics. That way I was always good at it. I was developing my aptitude for it as.
But I've been just saying, like half a step back, like how did you probably like narrow down on physics and mathematics? I mean, even was there like a story was there something that still made you?
Okay, yeah, it's not very impressive. So I talked to my mom, because my mom was when I was a child, she used to teach me, like homeworks and all that. And my dad was always there, but it was just like her passion to teach me. So I talked to her and I was like, so what should I do? Because she actually was a gold medalist from Sri Ram College of Commerce in maths honors in her time. She's like, do you think I should do math honors? And it's like, I think you will like physics more, because maths is too abstract and you have a lateral mind. And I was like, I did not tell her that I didn't understand what she said. But I said, let's just do physics honors.
Okay. But
so I did physics honors.
Just a quick follow-up on the St. Stephen atmosphere that you highly regard of. How was it in terms of experiments, and how was teaching experiments in St. Stephen's? Like, was it all about theory and being really strong in foundations, or did you also have some lab courses? Because
we did have lab courses actually.
But you will. But it's like, do you remember some lab experience that you didn't like, or?
No, actually, we didn't like the only part we didn't like was that the labs were at I think 3 to 6 p.m. or something. So all the college would be empty because no other courses had labs, and science students were were longer in college. But no, I think our lab courses I kind of enjoyed. I still remember we had a microprocessor lab, where we had to. It was like the precursor of computers, right? Like so we had to program them in assembly language programming.
8086.
Exactly. And then I really like digital electronics. Where we used to make circuits of breadboards, all the TTL logic and NAND gates, and all. I think that is probably one of the precursors which I thought about, which also got me eventually interested in quantum computing, because I had really enjoyed classical digital logic. But I mean, that was much different. And then I think but it is true, like, let's put it this way. So in St. Stephen's, I actually had this very interesting series, which was called Popley Memorial Lecture Series for street physics students. At least it used to be there, I don't know if it's still there, where they would call a scientist of great eminence, the Indian physicist, to give us a series of lectures. undergraduate students, even in first year. And when I say eminence, they are of the level of Ashok Sen.
Oh,
So
wow.
I still remember Ashok Sen gave a series of 3 lectures on string theory.
But did you understand Ashok Sen?
No, of course not. Nothing. But that's not the point. That's not the point. You're supposed to, when you're young, you're supposed to be like, all bright-eyed and be like these students. The point was to give exposure to physics students of researchers and research. And similarly, we had N. Mukunda talk about geometric phases. I remember, and I'm forgetting who was the third person. I'm sorry. But I remember there used to be this lecture series because, again, the intent of the college and the department was extremely clear that these guys are budding physicists. They may or may not want to continue physics, but that is our aim, to basically try to, and of course we had a long legacy of our seniors who had joined PhD programs. Because that's what we would hear about. I'm sure they might have joined some big banks also, because everyone does like all kinds of things. But I'm just saying what teachers would reiterate, this guy went to do PhD from Harvard. But okay, so coming back to your question, we did have lab courses, but the cool thing in Indian science was still theory.
Yeah, okay.
If you're really, really, really bright, you do theory.
Yeah.
So there was a different kind of class system. If you're really, really bright, you do theory. If you're not so bright and you still want to do physics for some strange reason, you do experiments. At least that was the impression I had at that time. Which of course was completely dispelled out when I joined PhD, but that was the point. And in fact, it is true that when I joined IIT after Stevens for physics and MSc physics, this impression continued because there were labs, but for some reason there was this, I can't even explain what was the reason. It was this vibe about experiments not being like cool enough. And when you are young, you want to do cool stuff, cool things. Money is not an issue. Cool stuff is the issue. Like, I want to be cool. I want to do some interesting things. So I think the first time I would say I really understood that experiments have a life of their own. And this is not just, okay, actually, the thing is, I didn't actually immediately join PhD in US at Yale. I actually was completely sure that I want to remain in India. So I had applied for PhD positions and what do you call that? CSI and CSIR exam and JEST.
Yes.
I had taken all those exams and I had cleared them and all that. So I had interviewed at ISC, Raman Research Institute, JNC, ASR. Because at Bangalore that was the hub, right? And so and I got through all of them. And again, there was this like, okay, I have interviewed for theoretical positions at ISC and experimental positions, and I was near the top of the list on the top both of them. I think I was in fact on the top of the list for theory, and everyone assumed I would do theory because experiments. If you're good, why would you do experiments? Right?
Okay.
But then the issue was that when I did, there are two issues which happened. The first issue, which was minor in the larger scheme of things, was when I interviewed after my selection in ISC, I asked them what kinds of theory you do, and the only openings were in soft matter. Everyone does theoretical soft matter or statistical mechanics or hard condensed matter, magnetic resistance and all. Right, the quantum information as a field did not exist.
But
there was one.
Just stepping back, like, were you so sure right away during your PhD that quantum information is what
No. So what I'm trying to say is there were only two theoretical fields which I at that time thought. One is more in like if you're like doing hardcore theory, string theory, or soft matter. Those were the two fields. And as I said, I don't easily develop aptitude for anything. I'm like, string theory, no. Soft matter sounded very simulation heavy to me. I didn't like doing those kind of simulation heavy things. I wanted pen and paper. But if you do pen and paper, then there was no middle ground, all the way string theory. So at least at that time, I'm not saying that was the case, but that was the case I felt that it had a very, and I don't think it was very far from truth. It was a very polarized thing in Indian theoretical science. That they were very straight-jacketed and very, very sharp boundaries between experiment and theory. So theory is more like string theory or soft matter, stat math, and experiment is, why would you even consider experiments? So that was the one thing, and I don't think frankly, in spirit of full disclosure, I did not like soft matter that much, just because it was very simulation heavy. I had actually done a summer project on it, and it's very simulation heavy for my taste. Like I said, sand pile models and all. Very interesting, but not for me, not for me. And so then but the main thing because of which I was not able to join IIC, I would have made peace with it. Was that my father actually unfortunately had an accident in that year. So he was bedridden for like 3-4 months. So I mean, my mother was still working, so we needed more hands at home. So I thought like, I'm not going to join this year. So next year we will see what happens. And so then I actually worked in Cambridge University Press as an editor for 1 year, just because I needed a job. And I said, why not? Why can't I? Because there's no point sitting at home and I will have fun. It was actually a very interesting job because I saw how books are published, and I was a science editor. So I think I read like 35, 40 books in a year. It was fantastic. I'm not and then my professors at IIT, they were like, yeah, you should definitely apply to US because you are interested in doing PhD or anyways taking a gap year. And there's no harm. You have not thought about this. You were thinking about India doing PhD in India, but for whatever reason this didn't work out. So while you're thinking about reapplying, why don't you just apply to US also? And that's when, during my gap year, while I was working with Cambridge University Press, I took my GRE while working at KCP and applied to US, and then Yale. I got accepted at Yale and I joined PhD at Yale, just because it actually had those. At that time, it was not called quantum information. They had mesoscopic physics. So I joined, okay, this sounds like the right mix of theory and still having things which I can think about in a much more, I think my mother was right. I don't like too abstract things. I wanted to do theoretical science, but still attached to the experiments. And of course, at Yale, it completely was a different scenario. Experiments were absolutely the glory and everything. There was no second-hand treatment to experiments. They had a life of their own. They were equally respected, sometimes even more respected in theory, in terms of if you see the high impact publications and everything, right? That was not the reason which motivated me, but that spell was broken, that unless you're not doing theory, you're not doing interesting things. So then I actually, of course, as usual, I was confused. So I approached my advisor, who was an experimentalist, Professor Michel Deborah, and I said, I'm not sure if I want to do experiments, but I want to kind of also do theory. So I joined his group, which is an experimental group, and did theory in the group of an experimentalist for some first 2 years, because Michel was looking for an in-house theorist for that time to explain the experiments. And then I liked experiments so much because all the group members would keep talking about them, that I thought, okay, maybe I should try my hand at it. And then I actually started working on experiments on Josephson junction and superconducting quantum circuits, and while also doing theory for them. And I really, really enjoyed that. Because to see your theory in action, the kind of high you get is very hard to describe. It's just, oh my God. I still remember the first time I saw a Rabi oscillation, I was like, oh my God, this is real. This is not just a calculation in Sakurai. This is real. It makes it somehow very real. It gives you a lot of physical intuition. I loved it. And so that's how that's what I continued doing in my postdoc at MIT. I did theory and experiments. And then eventually when I had to join start my own group as a faculty member, then I think typically it is easier to commit to one thing, at least when you are as a starting faculty. You don't have to. I had by at that time started enjoying theory a bit more than experiments. I still love experiments, so I started a theory group. But I have very deep ties with experimentalists still, to the extent that some of my students in postdocs, they actually work in experimental labs, even though they are my students, like remotely with my collaborators. But so yeah, so that is basically how it happened.
So, I mean, what amazes me is, I mean, as you say, the aptitude less and so on. And then typically, I mean, I'm an experimentalist and putting and trying, I have tried at various times, trying hands-on theory. It becomes a nightmare and then, forget it. And then I leave it and then I'm happy with the experiment. In terms of theory, I have seen people come to lab and they really get excited when they see, the Josephson IV curves in action. Look, they become excited. But then when you ask them to do a small thing or, and then they're like, okay, what's a multimeter? That's where it starts from. And then they have just no clue and then they don't have enough patience. But then this is really a very, you like both and you did both.
Yeah.
I mean,
and I think I was very lucky in terms of my mentors. Like I think my advisor, even though he's an experimentalist, a card-carrying experimentalist, he's probably one of the best theoretical thinking brains I have come across. So I think what happens is that if there has to be a genuine respect at the for this interface. I have also met experimenters like, oh yeah, theory is like putting a curve through my data points. I'm sorry, that theory is not about linear regression on our data. Theory has a life of its own, and so do experiments. And then I think truly big breakthroughs, really, I've seen that in my own life, right, in my academic life. They really happen at the interface. So I think because I have worked in the past on experiments, it has actually made me a better theorist for 100%. I mean, the kind of physical intuition you have when you are forced to think about, I can write on a Hamiltonian.
Yeah.
I can do some perturbation theory, do whatever. But when you're forced to think about what does this term mean, which you're writing in your Hamiltonian, what does this parameter mean? Which knob does this correspond to in a real experiment? The level of physical intuition which you can get by working on that interface. I'm not saying that this is necessary to develop physical intuition, but it's a very, very powerful medium to force yourself to think about, implementations. At least I personally really enjoy that. That is the reason that my group has the word engineering in its name. It's quantum engineering, science and technology, because we do both very fundamental theory, but we are actually very proud of how strong interface we have with experiments.
I'm reminded of Professor Phil Anderson, who said in, I think, one of his interviews that he never reads theory papers. He just reads experimental papers. So
I did not know that.
Yeah.
No, it's very apt. I think, but I think it's an acquired taste. I think people have to really try to be a bit more open-minded about doing that to themselves, because it's very charming to do only once. And I think at least that is the part which I now, in retrospect, I feel was happening in India, which is why I felt it so artificially contrived.
So you're basically answering a scientific question rather than calling yourself a theorist or an experimentalist or this or that. You're just saying, okay, whatever answers the question, you don't care.
Yes, absolutely. Absolutely. Exactly. I mean, if you look at all these great physicists, like look at Einstein, when his miracle, he did Brownian motion and photoelectric effect and special relativity, how would you categorize it? Yeah. So I think at least, okay, I'm not saying that we are in the 1920s. Unfortunately or fortunately, we are in the era of super specialization. But how much specialization you do mentally here is in your hands. Even while you're working in a field, how you approach a given problem. I think especially in places like quantum information, and I'm sure in other fields, there is a lot of leeway for you to talk to not just your immediate group members, but venture out, talk to other people, even in other fields, but at least experimentalists of your field or theorists of your field. It really also leads to better results. Just because, 1 like 1 plus 1 is 11 kind of thing that already happens. But I think if you have a fresh viewpoint, which typically happens depending on your background, I think it has always helped me. Most of my big results or important papers have been kind of accidental, I would say.
I think what you say is basically that we really need an open mind and just do what you like, and that's how.
And no, you should not let anyone convince you otherwise.
Right.
Do not think that experiments are second class and
Of course.
string theory is the only theory to do. If you are really genuinely interested in string theory, go for it.
Yeah.
More power to you, because there's some really beautiful work and very intelligent people working there. But do it because you want to do it,
Yeah.
not because it's a fad.
Yeah.
Or not because some 10 people before you have done.
So just moving on to it's really inspiring about how you have done various things. Now it's really difficult for me to hold back from asking you, what do you do? I mean, what
Okay.
research questions? Yes. So what research questions have you, how have you progressed, beginning from the PhD where you asked a certain questions, and what do you do now?
Right. So as I said, in my PhD, actually, I started working in Professor Michel Devore's lab. I first did theory. So my first few projects, and actually that was a kind of been an enduring theme, even into my postdoc, was quantum limited measurements and detection.
Mhm.
So the idea is that there is signal processing, which you can do at the level of classical mechanics or classical physics. But of course, in quantum physics, there are these quantum fluctuations. So even vacuum is never empty. So the idea of quantum limited measurements and detection was basically how to realize these minimum noise measurements. And it's kind of a minimum noise detection. So quantum metrology of sorts. And then, of course, I worked on experimental side on superconducting qubits. So people have been hearing about this, especially thanks to IBM and Qiskit. Everyone knows what is a transmon, or at least most of the people know what's a transmon. So transmon is not just the only superconducting qubit. There are several kinds. So I actually worked on the first fluxonium qubit, which is also a part of superconducting qubit family. And that's when I did actually experiments. And I ended up learning a ton of many body theory because we were trying to do something with that, which is beyond BCS.
Okay.
Which is the Baring-Koshiko theory of superconductors. That's what I'm saying. I was so impressed. Wow, in experiments, I can do this effect, which goes beyond BCS. So it was very interesting. So those were, because of when I was working in Michel's lab and then also in MIT, most of my work was geared more towards superconducting circuits. And also my theory was geared towards superconducting circuits, even though there are certain effects which are, as I was saying, have a theoretical life of their own. But since I have started my group, of course, I have taken all the liberty to diversify, and now we work a lot on engineered systems, because this is a part of a vestige of working with superconducting circuits, because you can really engineer quantum information systems. But we are also developing fundamental descriptions of ASMA, quantum cosmology, quantum thermodynamics. So surprisingly, as many of your listeners might know, in quantum information, one of the big things is error correction. So you want to build very coherent quantum systems. Unfortunately, quantum systems which exist in textbook are not how they exist in lab. You don't have an isolated harmonic oscillator or hydrogen atom to play with. They are typically what are called open systems. They interact very strongly with uncontrolled degrees of freedom or their environment. And because of that, they can die or decohere and lose their quantum information. So the idea of quantum error correction is very much like classical error correction, which we have in our current laptops, that if there is a fault, then there is some mechanism to correct for that fault. Like if a bit flips, if a 0 becomes a 1 or a 1 becomes a 0, then you can correct for it. And in fact, that is why you don't see so many blue screens in your laptops, right? There's error correction there. That's classic. So similarly, if you want to make any kind of quantum computer or even a coherent quantum simulator, not even a computer, you have to do error correction, in the sense that you have to correct for quantum errors. And that is a very interesting topic in itself, because quantum mechanics, of course, is different from classical mechanics. So it's not surprising that quantum errors are different from classical errors. And the usual tricks where you can see the system and like, oh, I see, this should have been a 1. It looks like a 0. I should correct it. You can't do that for quantum systems, because if you measure a quantum system or look at it, that actually itself changes the state of the system. So you have to do these kind of error correction things without really resorting to the usual tricks. So what we are doing, for example, is autonomous error correction, where the errors in the quantum system are automatically corrected for. So one of the things, the way we do it is what is called reservoir engineering, where you don't engineer the system of interest. You say, oh, I know the problem of this system is it interacts through all this environment, and that's what leads to errors. So what if I actually change the environment so that it doesn't lead to errors, but in fact helps the system? So in some sense, it's kind of the epigenetic approach to quantum engineering. The gene expression is not just set by the chromosomes, it's also set by the environment. So it's like we are basically changing the expression of the quantum system by changing its environment.
But
and of course,
just a quick question. But can environment be engineered in some sense? I mean, because doesn't it bring some randomness to the whole system? Isn't it supposed to be extremely spontaneous in nature?
So yeah, absolutely. But we take into account all these effects. But there's this very powerful results which actually show that if you can surprisingly engineer these environments, taking into account all the quantum fluctuations, and still make the system do what you want to do. And the reason for, I think it actually sounds weird, but it actually is not very weird, because if you think about it, you also engineer quantum systems despite the vacuum fluctuations associated with them, right?
Right.
Like when you engineer a harmonic oscillator, you know that there are vacuum fluctuations, right? Even in its ground state. But that doesn't prevent you from controlling it. It's just that we have just you change the viewpoint, because instead of fighting the environment, you are making it your ally. And so that is the idea of reservoir engineering and autonomous error correction. And in fact, amazingly, just this year, with our experimental collaborators, we were able to demonstrate it. So it is not just a theorist's dream; it's possible. So it was a very simple form where we actually made sure that we took 2 qubits, coupled it to an environment, which we engineered, and we showed, or our experimental collaborators showed, that the system remains indefinitely in an entangled state. Just because the environment steers it towards entanglement. Typically, environments are known to destroy entanglement, but you can arrange things such that they actually lead to entanglement. And this kind of entanglement is called is persistent. It's persistent entanglement because it's not going anywhere, because the guy which was working against you is now your friend. So it in fact reinforces it. So those are the kind of things we are doing from the point of view of engineered quantum systems perspective. We are also working with some string theorists and quantum cosmologists who are actually, amazingly, it's a complete turn of tables. They are interested in quantum information. So they are actually talking to us about how to actually model. Like there are lots of techniques which we develop for engineering quantum systems are amazingly relevant to early universe. And ADS-CFT formalisms, which people have heard about in terms of quantum gravity. Because all these systems are actually open systems. And quantum information theorists are, because of their job profile, are very used to thinking about these systems. So there is a genuine collaboration opportunity there. And in addition, we also work on localization physics, interesting many body simulation effects with quantum systems. So yeah, basically anything quantum, we are open to.
So you have, I mean, if I'm not wrong, you have seen the evolution of this whole subject to a quite a significant, it's a huge magnitude of change. For instance, maybe when you were studying, it was called foundations, and it was like what retired people do, like the quantum foundations. Whereas, I mean, sorry if I'm.
No, you're right.
And then now it's like everything which everyone wants to do, like quantum information. Maybe there will be very soon we will have high school kids doing quantum. Maybe they're already doing it on Qiskit or this IBM portals. Now you have seen this happen. It usually takes centuries for such magnitude. Can you kind of explain what do you think are the milestones, or how do you see this evolution, if you have to briefly see how the field sort of took off?
Yeah, I think it's a great time to really be in the field, enter the field for the right reasons, as I said. Curiosity is an absolutely perfect reason that I'm curious about these things. But as you're right, I think when I joined PhD, it was still a very nascent field. It was even called mesoscopic physics, basically because this was like somewhere between the micro and macroscopic systems. For the listeners who don't know what's the meaning of meso. So meso means that you have many degrees of freedom. So they are definitely bigger than microscopic systems. But all these degrees of freedom are still controllable, and they're pretty, they don't have as much noise as macroscopic systems. So in that sense, this was the field of mesoscopic physics. And a lot of that, and I think quantum information processing or quantum computing was still like a distant world for us.
Right.
And of course, now this field has completely exploded. I think there are many more resources for students to tap into if they are really interested in learning about this Quiz-Kit and lots of tutorials. As you say, I think it's both like slightly good and bad in terms of the explosion. It's a lot of opportunities. I think for students, it's only positive. I don't think there's anything negative. I think for practitioners of the field, I think we have to be a bit more careful about how much we shouldn't overpromise. But I feel that there is genuine, irrespective of whether you want to build a quantum computer or not, because that is not necessarily what motivates all the researchers, including myself in the field. But just because it really gives you a new viewpoint to think about how nature behaves at fundamental scales. It's really the new language of trying to understand microscopic phenomena, quantum physics. Like, in fact, there are now schools and universities, maybe not schools, but universities for sure, which are teaching quantum mechanics from a QI perspective, just because it's actually much easier to understand. Like sort of conventional quantum mechanics, if you actually take the language of quantum information to understand even a normal harmonic oscillator or a two-level system, it's actually I would say it is actually much easier to understand.
You mean it's more natural for us?
It's a much more natural language to think about these things. So I think as a student, as a young researcher, they should take advantage of all these resources. Do projects with researchers. You'll be surprised how open even senior researchers are to saying yes when you approach them. So do not hold yourself back and censor yourself in terms of the opportunities you can tap into. But yeah, I think they should not necessarily believe that they should join this field because they want to build a quantum computer in 5 years. That's not going to happen. This is something which is no real scientific breakthrough happens quickly. It takes a lot of hard work and real concerted effort. Think about like how much time it took us to reach here compared to when the first quantum equations were written. It was more than 100 years ago. It takes time. So, but I think it's a great time to be in the field. And I would actually encourage all the young, this is my like shameless plug-in. If you're interested in joining this field, please do, because we are always short of people talented and motivated who want to do great science. So do you see although we haven't yet made a quantum processor, but can you kind of see an estimate as someone who's in the field so much? Do you see this coming sometime soon? So there already, recently IBM has unraveled their 33-qubit Osprey processor. Yeah. So all these processors exist, but as you may have heard this term NISQ, we are in the NISQ era, which is these intermediate scale systems, but they're noisy intermediate scale quantum systems. So they are not the full-blown fault-tolerant error-corrected qubits. So that is why error correction is so important. And if you really need a coherent quantum processor, you don't need not only you need to have multiple qubits. You need them to be logically protected qubits. And so when people talk about these quantum processors, it's a great thing that they're building these big systems, but they are not error protected. So for example, if you have to make like you have these 64-bit operating systems, right? If you want a 64-qubit operating system, you need 64 logical qubits. And with gates which are also logically protected, which means like, if you want to do an AND gate or something about between two qubits. And there have been estimates, if you do these estimates, you run into easily tens of millions of qubits, because the overhead of having error correction, not only on your qubits, but to also have error corrected gates, which means the operations between those qubits are also error corrected. Which means if you are saying that I want to do this gate on this system of qubits, and that gate should be basically have no errors. And on top of that, it should be fault tolerant. So for example, if I do some error here, it will not propagate and grow, lead to a whole avalanche of errors in my entire algorithm. When you take into account all those effects and you calculate what is the system sizes you need, it's tens of millions. So that's what I'm saying. So even if you don't want to build a quantum computer, you shouldn't feel, oh my God, it's a lost cause. What's the point? We'll never get there. That's not what we're saying. The point is that there's already enough sophistication in quantum information platforms that we are very far from building a fault-tolerant quantum computer, but we are already there where we have sufficiently big systems where you can do some really beautiful quantum simulations. I mean, that was the original dream of Feynman, right? Quantum simulates quantum. So we are already there where you can unravel some really beautiful physics with these systems because of the exquisite control capabilities we already have. So I think for a processor, maybe a few qubit coherent processor, I think that can happen within the next 3-4 years. I mean, it's already happening. Interesting in terms of more connectivity that's going to keep going on.
So I have one last question from my side. It's more to tell us something about your path and being a female researcher. You have been in niche places, and you have also done mathematics and theoretical physics, where number of women are really less. And now you're one of the leading persons in this field. Being a woman did it come in your path that you belong to this gender?
So, I mean, well, there are several aspects about this. Some of them are more sociological and some are personal. I think the sociological aspect is always there. I mean, anyone who has been in IIT, even for a master's, they know the gender ratios are completely skewed. Right? There are very few women as compared to men. So in some sense, that automatically, obviously, kind of, it's very hard to explain why it is weird. I was once having this question. I once posed this thing to my husband. It's like, just imagine going into a department where everyone is a woman and you are the only one. You are the only man. That's how you would feel, right? And it's like, yeah, that's super weird. Like, that's exactly what happens. It's not that someone has to be bad to do something bad.
Yes.
It's just weird. It's just weird because it's just like, we, how do I say this? It's, we all want to be different, but we don't want to be an outsider in some sense. And it's just like, this idea of imposter syndrome, which I'm sure this is a gender neutral phenomenon. All men, women, different ages, they all feel that. It's just that for women, it's a bit more enhanced because it takes you longer to get a sense of belonging anywhere because you don't have many people who look like you, in some sense. So it just compounds it. I'm not saying that it is easier for men. It's just maybe a little weirder and harder for women. So that is definitely the thing which is always there. Of course, my professors at Stevens and IIT and then Yale, they were super supportive. Well, okay, all the professors are supportive if you're a good student, but I'm just saying. So that actually helps. But I think it is still a little like, when I joined my group, Michelle's group, it was very, he was a great advisor, very supportive. But again, all the members were males. And in fact, not only our floor was all male, all 3 floors of the building were. So, so it's just a sense of community is just a bit limited, I would say. That can be a challenge. Thankfully, things are changing in QI. They're not maybe changing fast enough, but they are changing. But I would request, especially the women listeners, to kind of just like slog it out. Unfortunately, try to find people, maybe even outside your department, if you feel a bit lonely. I mean, research is a lonely enterprise, period. When things are not working and you are sitting and scratching your head, whether you are in a lab or in a theory office, you are alone.
Yeah.
It's just that feeling of loneliness can get intensified. But then I think other thing is that after becoming faculty, I'm seeing now this in a different light, because I can now see, from the other side what it looks like when I see 1 woman or 2 women in my class. I unfortunately, like, there is 0 women in my group except me. So that I don't know what to make of it. But I think so. It's not. This is a myth, according to me, that women tend to join other women just because you are a PI who is female. Females will want to work with you. That doesn't work that way. I think it cannot be changed at the group level. It is a systemic culture in scientific fields which has to change. I don't know how to change that actually. And I would say, in fact, it's worse if you go further up. I would, in the sense that it's like a pyramidal decrease.
But in your groups, like, just curious, do you get very less number of women applicants, or?
So first of all, exactly. The number of PhD applicants who are women are already less. It's a major cut. Right? In BSc, they were like, I would say 50-50. In IIT, they were like, I think 4 women. We were 4 women out of 35. Then in PhD, it was, I think, 2 out of 16 or 17. And then but the issue is that already there's a big cut at the level of PhD. And then few women who do come, somehow astronomy absorbs all of them. I don't know what is it about astronomy. Why do people want
to black hole there absorbing?
I don't understand. I genuinely don't know. So my running theory is that I think astronomy as a field has done fantastic on outreach. They have these really beautiful efforts. Okay, it's very hard to compete with a picture of the Cat Crab Nebula. No matter how fancy you show a dilution refrigerator or quantum processor, it doesn't have that feeling. So I mean, we have to work with what we have got. But in addition to that, I think as a field, we have not done enough outreach. We should be doing that more. All scientific fields should be doing that more. This liquid nitrogen ice cream is not good enough. I'm just saying. So I mean, come on. You have to make it look cool. And we have to somehow. This is my pet peeve. I don't know how to change this. I think there is this genuine problem of damning the women with faint praise. I have seen this. Not to myself, but because I don't know for whatever reason I was lucky I escaped this or whatever. That there's actually genuinely not enough high expectations from women. In the sense that if you're not doing well, oh yeah, it's fine. No, it's not fine. You are actually capable of better than this. Don't settle for something. And I think this is something, I don't know, I did not feel that. I definitely see that in US universities. You're not supporting them by lowering your expectations. Just because they are lonely, they need more support network. They don't need lowering of expectations. The competition level should never be reduced, because I think eventually it hurts everyone. So that is the part which I have definitely feel, at least in US universities, that somehow because of the weaker sex or whatever, fairer sex, all these are super race systems according to sex systems. There is a genuine, I think I was actually very lucky in the sense that I worked with a person, graduate student who was 1 year senior to me when I was in Michelle's lab. He's now at IBM. I'm not going to name him because he will be embarrassed, but I'm praising him, so it's okay. So I don't know, people who have worked in the labs, they know that you have to, in these dilution refrigerators, they work on a helium-3, helium-4 cycle. So you have to transfer helium. And that's very acrobatic. It's a very acrobatic thing that you have to put in the helium-4 and you have to transfer liquid helium-4, and it looked very intimidating.
It can be scary when you
the first time. And he was like, so he was training me because he was my senior graduate student, 1 year senior, and he was just like sitting there, and he's like, the first time you are doing it, you're like, oh, I have to wear gloves and I have to wear my goggles, safety goggles. Like, what are you doing? And he's like, I'm just preparing to transfer helium-4. And it's like, it's just transferring helium-4. Just go and do it. You'll be fine. So he pushed me very hard in terms of overcoming my fear, because I was very iffy, because also in India, girls don't do household work. If the bulb is gone off, like a father or brother will change it. You don't do hardware stuff enough. So I think it was very important for me to actually have him as my main trainer, because he was like take no prisoners kind of attitude when it came to working in the lab. So I think that is the one thing that you might actually face a lot of doubt from within or from outside, and don't let that bog you down. It's I don't know how to fix it, frankly. It's just that I try my best as an instructor, but I've seen that women have a much, much higher probability of doubting their capabilities. And the environment doesn't help. And that is, I think, the main hurdle. I mean, we already have a problem in numbers, but the people who even make it and make the cut, they are very deeply doubtful of their capabilities. And that doesn't help, because, you really need some kind of I think Daniel Kahneman says this in Thinking Fast and Slow, that you have to have delusional self-confidence, not just self-confidence. You have to have delusional self-confidence about your capabilities when you're working in research. Because that's the only thing. You do not know if it will succeed or fail. And so if you keep doubting yourself, you will, it's like, it will become true. If you keep thinking it will fail, it will fail. Because you will just have this self-limiting characteristic. And I think for women, they are somehow the society and the sociological setup of science, the low numbers, this certain people who just are lowering expectations all the time, just because you're a weaker person biologically or whatever. It just compounds all this. And I think that is the main thing which they should overcome somehow. Yeah. But I think it's possible. It's possible. Just stop listening. Just be pig-headed. You'll be fine.
Since we are coming towards the end of this discussion in terms of time, anything that you would like to add at the end as a message to people listening to the podcast?
Join quantum information as a researcher.
Everyone do quantum.
Maybe you will love it. Maybe you will not. But give it a shot. And joke about it. Just do what you love. I think that makes life very simple.